Hello, I am Kobayashi from Sony. In this tutorial, Guidelines to determine the number of layers and neurons, I will explain the thinking behind determining the number of intermediate layers and the number of neurons in a neural network. In the previous video, Basics of Designing Neural Network, I explained that the number of intermediate layers and the number of neurons were optimized on a case-by-case basis according to the problem to be solved. Here, the number of intermediate layers indicates the number of times that artificial neuron calculation is repeated from input to output. The number of neurons in an intermediate layer indicates the number of neurons that is to be prepared for each layer. Basically, the more you increase either the number of these layers or the number of neurons, the more you increase the power of expression of this neural network. In other words, you could say that this makes it possible to solve more difficult problems or achieve a higher level of performance. On the other hand, when the number of neurons or the number of layers increases, the number of data samples needed to train the neural network, the amount of memory needed to make calculations, and the amount of computation increase as well. In some cases, insufficient memory may prevent training on the computer, or an excessive increase of computation may cause the execution of training or the execution of a trained neural network to be extremely slow. Here, we have some guidelines for determining the number of intermediate layers and the number of neurons. Setting the number of layers and neurons according to this theory allows you to achieve a high level of performance efficiently without increasing the amount of memory or computation more than necessary and without increasing the required number of data samples. First, let's look at the guidelines for determining the number of neurons in intermediate layers. As for the classification problem, basically, you make the number of neurons large immediately after input and then gradually make it smaller. This is the neural network that was used in 2015 to exceed human perceptual performance for the first time in ResNet 152 image recognition. This indicates the input data 3 by 224 by 224, which means that this is an image that is 224 RGB pixels high and 224 pixels wide. This neural network's output is 1,000 neurons. 1,000 neurons that indicate a variety of categories are the neural network's output. The number of neurons from input to output is represented horizontally in the graph. Convolution is used immediately after the first input, and 64 images measuring 112 pixels by 112 pixels are processed. After the images undergo max pooling and are processed to 56 pixels by 56 pixels, convolution is used to process them to 256 images measuring 56 pixels by 56 pixels. You can see that res unit is written here. One unit is a 3-layer convolutional neural network. So, there are 3 units of 256 by 56 by 56. In other words, this is a 9-layer convolutional neural network. Then the images are downsampled to half of their size. They become 28 pixels by 28 pixels in size, and the number of images doubled to 512. In this state, we have a convolutional neural network with 8 units and a total of 24 layers. The images are then downsampled again to 14 pixels by 14 pixels, and there are 1,024 images. This means that we have a convolution layer with 36 units and a total of 108 layers. Finally, the images are downsampled to 7 pixels by 7 pixels, and there are 2,048 images. Here we have 3 units and 9 layers. The network is structured to categorize into 1,000 classes. As you can see from the figure, the number of neurons in the first layer increases sharply, then decreases quickly soon after input, and continues to decrease gradually as it moves toward output, so the structure looks like an upside-down triangle. You will be able to determine the number of neurons according to the theory if you keep this shape in mind when determining the number of neurons for each layer of the neural network. The key points to keep in mind are that when you have downsampled to half of the size vertically and horizontally, you use max pooling, for example, or convolution stride, and when you have reduced by half vertically and horizontally, you'll need to remember to double the number of images, in other words, the number of maps in convolution. The reason is that when you have downsampled the image resolution to half, the number of neurons is reduced to half vertically and horizontally, which means that the number of neurons decreases sharply to 1/4. Now, when the resolution has been reduced to half vertically and horizontally, if you double the number of images, you can cut the number of neurons in half each time without sharply decreasing the number of neurons by downsampling the images and increasing the number of images at the same time. You can see that in the actual ResNet 152, the number of images doubles at the time the image resolution is cut in half. This is the theory in the case of the classification problem, but on the other hand, there are also neural networks that generate images. In such cases, basically, the number of neurons is gradually increased, and the target data is generated from a number of neurons that is much larger than the data that is ultimately to be output. When designing a neural network, you can decrease excess trial and error by checking whether this type of theory is being followed at the design stage. For example, in the case of the neural network console, the number of neurons in each layer is displayed to the right of each function in this manner at the neural network design stage. This graph is similar in shape to the figure I showed earlier. You can check whether or not the theory is being followed by checking whether or not the configuration is such that the number of neurons increases immediately after input, then gradually decreases. Once the number of neurons in the intermediate layer is at the optimal level, you may want to adjust the number of neurons if you subsequently acquire a large number of data samples, for example, and want to conduct training with more data samples, or you want to apply the same neural network to a new problem for which there are few data samples. In such cases, you can conduct training with new data from a state that has been optimized to a certain degree by increasing or decreasing the number of neurons throughout the entire network while maintaining the ratio of neurons in each layer. For example, if you know that this neural network at the center has been optimized to a certain degree, in order to apply it to more data samples, you will need to increase the neurons in each layer by the same ratio. In the case of a convolutional neural network, it will be the number of images. For example, if you want to double the number in each layer, you can start from a status that has been optimized to a certain degree if you increase the number of images in each layer by the same ratio, 64 to 128, 256 to 512, and so forth. In the opposite case as well, you can conduct training from a status that has been optimized to a certain degree by cutting the number of neurons in each layer in half, for example. I will now summarize the guidelines for determining the number of layers and neurons. As for the classification problem, you increase the number of neurons in the first layer and then gradually decrease it. Keep in mind that you need to double the number of images when you have cut image resolution in half vertically and horizontally to prevent rapid changing of the number of neurons. On the other hand, in the case of the issue of generation, you gradually increase the number of neurons from a small number, then finally compare it with the output data and create output data from a significantly large number of neurons. You can achieve a high level of performance relatively easily by first beginning from a small number of neurons and layers, then increase the number of neurons and layers according to this theory. When increasing or decreasing the number of neurons during the process of trial and error, you can do so while maintaining a configuration of the number of neurons that has been optimized to a certain degree by doubling the number or cutting it in half throughout the entire network while maintaining the ratio of the number of neurons in each layer. As I discussed in the previous video, Basics of Designing Neural Network, although there is no right answer regarding the number of intermediate layers or the number of neurons, but following these basic guidelines should allow you to design neural networks quickly and efficiently.